and we are going to solve a new problem again, and this problem is something unusual about this. So let me read the statement of the problem that says a platform mounted on a vertical massless spring performs a steady oscillation. The platform is performing oscillations. Okay, a steady oscillation, that means free oscillation, that means undamped oscillation. It is oscillating. So the spring, so it will have an angular frequency and it will have a time period. So platform will have some kind of mass. The spring is massless, but platform can't be. So, and the next statement of the problem is at the moment the platform passes through its equilibrium position. A small ball falling from a certain height hits it elastically. That's fine. And after the collision, the velocities of the platform and the ball remaining unchanged in magnitude. So, there is no use of writing conservation of kinetic energy, because we will find nothing from writing that equation. So our one equation is already gone, and change their directions to the opposite. Oh, mechanical energy conservation can do something, because kinetic energy conservation has no scope to do anything in this problem. It will not even provide a single equation to us, so it's of no use. It is equal to it is simply like writing a identity left equals right, and it gives nothing. After some time the ball hits the platform again at the moment it passes through its equilibrium position. There is one problem. In between this time period, platform is completing its oscillation or not. That in one time period of oscillation of platform, there will be two collisions or maybe more than two collisions. I don't know. This problem doesn't clearly states this, because it is not clear. That means ball hits, it goes up in the air, comes down, it takes some time, and then it hit again, and the platform is again at its equilibrium position. And in between, what happened? It may have completed some oscillations. It can be. So I'm assuming this. Assuming that the maximum deviation A of the platform, this is about platform, that is the amplitude of the oscillation A, and from the equilibrium position and the period of its pre-oscillation T are known. Oh, for the platform, these things are known. Find what the ratio of the masses of the ball and the platform can be. So I can write, suppose the situation is something like this. At the initial moment, the platform is moving with some kind of velocity v, and ball is coming to hit down with velocity v. And after collision, the ball reverts its velocity and the platform as well. It happens. So I can write a conservation of linear momentum here, and for this I took the positive x-axis downward, and before collision I can write the momentum of the ball as mv and momentum of the platform as minus mv, and it gets reversed simply after collision. So I can write this equation, and this equation gives us the ratio of masses of the ball and platform, and that will be simply v by v. So inversely proportional to their initial velocities. So we need to find out the velocities of the ball and the platform before the collision. How can we do this? We have only information. The ball will spend its time in air. That means just after the first collision, ball will go up in the air and coming down to complete its one cycle of motion. And during this whole cycle of motion, time spent by the ball in air is simply 2v upon g. This is the time of flight of the ball in air. But on the other hand, the platform will go down, yeah, and it will come again. No. Platform will go down and it will come again, and this time is half of its time period. And then what happens? Then it will go and complete a full cycle to come again in this position. And how many full cycles it will complete, I don't know in between. So this time and full cycle of I just assume that there are n number of oscillations of the platform in this time t. So this time t can be simply written as t by 2 plus nt. N I don't know, and it was not given. And of course we know t can be written as 2 pi under root m by k, because its angular frequency will be simply under root k by m. And after equating these two equations, we can get the velocity of a small value of small b at least, and this small b value will be gt upon 4 multiplied by 2n plus 1. So this is the velocity. And how can we find the value of capital V, that is the speed of the platform before the collision? Oh, we can use the conservation of mechanical energy, because its amplitude is given. So I can write here half ka square equals half mv square simply. And this v is very much known to its omega into a, and that is we don't need to, could have simply written v will be equal to omega into a. And but k or m are not given, so we can use this, and we can find here under root k by m equal to 1 by t. So we can write here 2 pi by t. 2 pi by t. This is omega and this is 2 pi by t, nothing. So I can write here a by a 2 pi a multiplied by 2 pi by t. So this is v equals this omega a. Omega is 2 pi by t into a. We don't need this. We don't need this whole thing. We can simply write this v equals omega, that is 2 pi by t into a, and we could have gotten this equation earlier. And I think I can solve the problem. M by n can be simply written as capital V by small v, and that is 2 pi a by small v multiplied by t, and that will be simply putting all those values. We can get m by m equals v by v equals 8 pi a by g t square 2n plus 1. N could be anything, because it is not given in the problem. It could be anything. I don't know. Thank you very much for watching.